Hello everyone. Let's continue with question 10.2 on maths. So 10.2.3 is, we left off at 10.2.2 where we proved that G1 was 90 degrees, and now we're looking at 10.2.3, which is asking us to prove that CD squared is equal to CG multiplied by DB. For you to be able to comprehend all what we're going to do here, please have a look at the previous video. I'm going to attach the link to it along this one. So one important thing that we did on the previous question is to prove that the triangle FCB is similar to triangle CDB. All right. I told you that there's three ways of proving, or there's three bases on similar triangles. You can go with the angle side, with the angle, prove that there's two angles that are equal on the specific triangles, or we can go with the sides. So sides is purely proportionality. Or we can mix angles plus side. But the good part is that if you have proven that the two triangles are indeed similar, then you can use everything. You will know that everything is true. Angles, there should be angles that are the same on either triangles. The specific sides along those specific angles, they should be proportional. So what we see on this question is the CD squared, then the CG multiplied by DB. So let's ask ourselves, where do all those sides fall in? Okay, CG, this is CG. There is also DB. DB is this one. And the last one is CD. So CD, so there's DB, then there's CG, then there's CD. Okay, so I've told you about this one. This is the way we proved similarity. And by the way, we see that one of the triangles in here was involved in this proof. But we see that so CG already tells us about this specific triangle, and this was not the one that we used to prove that we were working with FCB there. Okay, so what we see in that statement is that, okay, CD, if you had to expand the statement, it looks like this. Okay, let me just write it here. CD, I need a different color. CD times CD is equal to CG times DB. Okay, so somehow we have a multiplication of two sides, and then we have two sides in here that exist on different triangles. CG is on this, so CG forms part. Okay, let's say CD forms part of triangle, let me call it CDG. So CG forms part of that triangle, and DB forms part of CDB. So this triangle in here. Then we've got CD. You see that CD forms part of this triangle, but it's also, you have to be very much observant in here. Or to make things simpler, okay, CD forms part of this triangle, but it also forms part of this one. So if we were to separate the two triangles, we have a triangle that looks like this. And then we have a triangle that looks like this. Okay, I'm going to use a different color. So this triangle is CGD, and then this one is our CDB. Do you see that this is also in this triangle? So CD is one that forms part of those triangles. So we can already see where this links up to, because the only way you can link two triangles is if the two triangles are equal or if they are similar. So similar being that we lean more onto proportionality. But like I said to you, for you to speak of proportionality or speak of similar triangles, you need to prove firstly that those two triangles involved are indeed similar. You have a variety of ways to prove that, so go and look at how we proved this one. But the most important part I told you there is that before you venture into using sides to prove that triangles are proportional, or use sides and angle, be careful or make sure that the sides at least help you to figure out proportionality. In this case, we still see that all these sides don't have numbers attached to them. But what is important about these two sides is that there's plenty of angles. So let's go on to prove that these two triangles, so these two triangles are similar. In these two triangles, we have angles, there's C3 here, then C2, and then D3, D2, and so D1 and 2. D2 and 1. Okay. So let's prove that those two triangles are similar. To prove if triangles are similar, we have a variety of ways, and we're going for the angles side in here. Okay, so the first thing is, what is special about this triangle? What is special about this one? Remember that, so there's G2 here. Remember that on the previous question, we were proving G1. So just try to look at the previous questions and how did you solve them, and anything that you might have solved in those questions, check if they are anyhow linked to the triangles of interest or the triangles that you're working with. So we already see that there's G1. And G1, if G1 is 90 degrees, we can already tell what G2 is, because this is a straight line. Okay, so we already see that this triangle here has a 90 degrees, which we can call a right-angled triangle. We have to state that in there, but this is the part of observation. So we know, yeah, we may write that down or just pinpoint it here. So this must be 90 degrees. But also we've proven that CDB also has this 90 degrees. We calculated this when we're proving this guy in here. So that is also a right-angled triangle. All right, let's go. So we can already see that we already have two angles that are equal. But the first one, G2, is not given. We already calculated this one. G2, angle G2 should be equal to 90 degrees. Or the best way, you can either say perpendicular, so this line being perpendicular to this, or we can go with G1 plus G2 should be equal to 180 degrees. These are angles, straight line. So just going to summarize it, straight line. So we already have the value of G1, so we can find G2 by taking G1 to that side. So 180 degrees minus the value of G1, G2 is equal to 90 degrees. But we can already see that G2 is equal to DCB. Therefore, G2 is equal to DCB, equal to 90 degrees. So let's note it there. So that is angle C2 and C3. So please, let's update that. I'm just gonna put it in like that, and maybe put one this side. Okay. So we've proven the first part. So in these two triangles, this angle and that one are equal. Okay. Another thing is we are not done. We've proven one angle. We need the last angle. So you look again. Okay. This triangle C2 has this angle here. So we can either try and prove maybe this angle with another angle in here, or we can go for this one and maybe this one. But you'll see, you'll figure out which ones are the quickest. So that is just the starting point. So if we observe this line in here, we know that there's already that 90 degrees. And let's ask ourselves, what else can we benefit from this calculation? We can definitely know that this angle D2 can never be equal to this angle here, that is D1 and D2. So this is you cancelling certain angles. So because D2 is not equal to this one, it means that we must prove that D2, because that's the only angle, because we've eliminated this one, then D2 should be equal to this angle, C3. Or you can do it the other way around. D1 plus D2 not being equal to this one, it means D1 and D2 should be equal to that one. So, because these are angles, we're trying to prove that these triangles are similar. So, which is the fastest route? Do we have the value of P3? No. Do we have the value of C3? No. So, which is the fastest to solve? Okay, one important thing is that there is a line here coming from center O to D, and there's a line coming from here O to C. These lines are called radius. So these are radii. These two lines are equal. So it's a radius. It comes from center, touches the circumference. So you add that as part of your thinking to solve this. Now, because those two lines are equal, remember, this is also a triangle. And if a triangle has two sides that are equal, it means the opposite sides are equal. This is an isosceles triangle. How did I come about that? This is you utilizing all the information that you've used. You could have went to the other side and said this line also is a radius in this one, but you were only going to figure out C2, that it's supposed to equal to P3, but we're not looking for C2 in this case. So therefore D2 should equal to D3. D2 should equal to C3. So D2 should equal to C3. So that's the first part. D2 equals to C3, and then you put the reasoning. So if D2 is equal to C3, so we can see that this D2 here is equal to C3 in here. So the reason is that it's an isosceles triangle because OC is equal to OD. So those are two radiuses. So this is a radius and a radius. So two being equal, it means the opposite angles are equal. So since we've proven that there's two angles that are the same, so this one is the same as that one, this is the same as that one, it means these two triangles are similar. Those two triangles are similar. Okay, don't have much board space now. Let's erase this, but we've proven that indeed this triangle Alright, we have proven that triangle CDG is similar to triangle CDP. So if those triangles are similar, you look at the end. So if these triangles are similar, then you can start using proportionality. Why am I doing this? Because the very first point or the part of the question was about proportionality. Because in here, you see we're only dealing with sines. We're not talking of angles. So they're trying to make us figure out how to form that equation. And for you to form those, you need to follow the process that we've just illustrated to prove that these are similar. Then from there, you can start using proportionality. So because those two angles are similar, it means specific, so all the sides are proportional. But which side is proportional to what? How do you locate the sides? So you see that there's a right angle here and this one. It means, so your what is this? I'm gonna try to note it with this one. So you find sides of interest. How do you find how to shape this triangle? So C or CG here is a line that is between this guy and this one. So it means you can put a note in here that this line should be proportional to this one, because you are using the angles as your direction. Then, since you already see that, we already see that then DG is the opposite line. So the opposite line. So this is the line that is not. So this is the line that is directly. What is this? So there's opposite. There's opposite. So let's say if you look at this triangle, in here is a right angle triangle. This side in here is the hypotenuse, adjacent, and then this is your vertical, or the line that is, we call it the y-axis. But this line in here that is directly or not adjacent to this one, this line should also be the same also in that triangle. So you look at your 90 degrees, you don't go adjacent, you go on the opposite direction. So it means this line is the one that's proportional to this one. Let's name them like that. Okay, then the others, it should be true also. Okay, let's go. So this is how we do our proportionality theorem. So CD of this triangle, CD over which other side is equal to this one is proportional, CG. So if you were to take this side, divide by this one, the factor or the value you're going to get there should be equal to the other sides divided by the corresponding ones on the different triangle. So you have CB divided by C or DG. And then equals to the last one is going to be this one, of course. So it's going to be your DB over CD. So you see that is your proportionality. Then you ask yourself, this form here that we are supposed to prove, which side are of interest? So we see that CB is not in that equation. DG is not in that. So we're mostly interested on these two lines. This guy is there, this is there, CG is also there. So we do this. CD, we eliminate this. We're not saying it's wrong, but we just eliminate it because we want to form that equation. CD over CG should equal to DB over CD. And if you cross multiply this, because we're supposed to form CD squared, cross multiply this, CD squared should be equal to CG multiplied by DB. You have proven that indeed that equation is true. This is an iterative process. It is a slightly hard question, but I don't want us as this group to use the word hard. It just wants you to imagine more, practice more, and ask more. Ask a question. Is not wrong to not know something. Ask it now. Don't ask for the answer. Ask for the method. Ask for, or try to see the person who's explaining it to you. What is their thought process? How did they imagine all of this? Or how did they manage to combine all these lines and make sense? That's all you need in circle geometry. Look at the lines, look at the shapes, make sense of them. Let's go to the next question. All right, the next question is asking us to prove dp is equal to cg plus fp. And the most important word they used here is hence. They said hence or therefore. So they are saying on the previous question that you've just calculated or just proven, use that, or that should form part of the answer that you're going to use in proving this one. All right. Again, the same process. What are the lines in there and which triangles do they form part of? So DB is still in that same triangle we're working with. CG is the same, but FB is on this triangle. Okay, so FB is on this side. It gets a little bit tricky now, but what they are saying is that try to use that as your basis. So you're dealing with two triangles now, three triangles. There's this triangle, this one, and this one. So let me name the triangles. It's your triangle CDG. It's your triangle CDB and triangle FCB. Okay. What is important with all these triangles, or what is one similarity, or what is one thing you can pinpoint? We already know that these two are similar. We are not sure if this one, let me see if we've proven. So the previous question, oh yes, the previous question asked us, yes. So question number 10.2.1b, or the calculation for this is on the previous video, the video that you should watch before this one. So we proved that this FCB triangle is similar to this one. So all these triangles are similar. That's one thing you should note in here. And the most important part is that all of them, they are right-angled triangle. Right angle. Why am I using that? Because on the previous question there was a multiplication. Multiplication means that there is proportionality. You have to cross multiply the two signs. But here there is an addition, and the only part you are going to form this addition on is if you go or use the fact that there's right angled. And right angle, we know that we have the rule for right angle triangles, in that the opposite angle, so there's opposite side squared equals to adjacent. So I call it, okay, let's use a quick drawing here to make everything simple. A right angle triangle, if this is your R, which is your hypotenuse, there's going to be X and then it's going to be Y. R squared should be equal to the summation of these two. So X squared plus your Y squared. So I can imagine that because there is the plus in here, we should link this to the fact that there's right angles. How we're going to do that is what we're still going to figure out in this triangle. But the most important part is to see, okay, which part links to what? FB, we see resonate with that triangle. CG is on this triangle, and then DB is on this one. Okay, so let's figure out how these get in. But we already are told that we must use this guy. So we can already see that we have a leeway here, in that we are not supposed to, it's fine, we may not consider this triangle because the one side CG that is on this triangle is what we're going to get in there. But FB in here is going to make things a little bit exciting. So let's see. In here, there's gonna be, so let's start with these two triangles. So let's start with CB. So this is our hypotenuse, which is DB. squared. This is a right angle. And then for right angle, we have that CB squared plus, so both of these sides, CD squared. Those, that should stand because that's the rule that we're using in here. I've tried to include both of the triangles. So basically, if you look at DB, so DB squared, we have included CD squared here, which we've already proven on the previous question. So we see that we can already substitute in here by CD squared. All right. So, and also we have DB. The one thing we don't have is FB, and we don't know how FB links to all of this. So we need to figure out how FB links to everything in there. So FB is in this triangle, and we've proven that these two triangles are proportional. So it should stand also that if we were to do the same formula for this one, so say hypotenuse CB squared, which is this one, should be equal to FB squared plus FC squared. All right. So that's the first thing. But you see now we've included FC, which is not part of this equation. So we might be going with the right root in here, but it's including another variable which we don't need. We know that CB is already part of that one. We know that FB is part of what we're trying to prove, but FC is adding to our problem. So we might be going the right route, but we might need to change the direction because the route that we're going with is going to cause more complication in the future. So what other route do we use? We have proportionality. Proportionality, we know that FB, FB, so we've proven that this, so FB on our previous video, FB over, so you look at which side is that forming. So it's FB is here, so there's that angle here which form part of this one, or this one. So FB divided by CB should be equal to, so now we go for CT. So FC over CT and that should also be equal to CB over DB. So that's that. It's gonna be your CB. No. Okay. So we have FB over CB, and then we have FC over CD. Then the last one is our CB. The CB though that forms part of this triangle. So CB over DB. And we already see that the reason why, so we went to this triangle and we see that it included this variable that we don't need. Then we already see here that if we were to continue with that route, this one is also going to cause more troubles for us. So we focus on this one. So those two, we have a relationship that we see there, that if we were to cross multiply now, why am I doing all of this? Is so that we can start including the variable FB to our equation here and hopefully use this standard equation to figure out how DP can be the summation of that. So it's not an imagination, it's just using the tools that we have available to your advantage. So FB, DB multiplied by FB are going to be CB squared. Alright, so that's another thing we've just discovered today. So DB times FB is equal to CB squared. So because of post space, I'm just going to put this equation at the top here. So DB multiplied by FB is equal to CB squared. Alright, now we're getting a little bit closer to our equation. We've figured out the value of CB, which we don't have in here. So we need to substitute CB by one big chunk that is going to at least lead us to that proof. And also CD is not part of this, but we already know that it links to the previous question. So we need to substitute on this one, CB, and we also need to take CD here and substitute here. So DB squared equals 2. So if you substitute at the place of CB squared by this one, you're gonna get an answer of DB multiplied by FB. Plus, in the place of CD squared, you substitute by what you are getting there, which is CG multiplied by DB. Okay, at least now we've eliminated all these unnecessary variables, and we at least also have the sides of interest in here. How are we going to take this and get to this part? So the most exciting part is that DB squared is just DB multiplied by DB. And we can already see that DB is a common throughout this time, throughout that equation. So we can divide by DB. And what you do on the left hand side, you have to do on the right hand side so that the equation still stands. If you divide here by DB, divide by DB. What this means is that this DB will cancel one DB, this cancelling this, this cancelling this. Why did I have to cancel one DB there? Because this equation that we have here is not in the squared kind of format. We are talking of 1 dB, which is not 2 times. And then, so therefore, we are left with dB here equals to FB plus CG. We have proven that indeed that statement is true. I have to rate this question as a little bit difficult, but it is, everything is possible in here. You just need to practice a little bit more. And if you have any questions, please drop them in the comment section below. Thank you, guys.